Hi, this is Dr. John Bergduff again. In this video, we're going to continue our discussion of graphing polynomial functions. But this time, I want them to be a little bit more general. The ones we've seen already fit into nice, neat little packages that you could graph using techniques about shifting and stretching and reflecting and those sorts of things. The ones I want to look at today don't seem to fit quite so neatly into that package, and I want to take a look at some like that. So I'm going to switch my camera a little bit and kind of give you an idea of what we're going to look at. Give me just a second here. So I want to show you, first of all, an example of the type of thing I'd like to graph. I'd like to sketch the graph of this polynomial function, and you'll notice that it is a good deal more elaborate. I don't immediately just see a shift and a stretch. But I do want to tell you that if you use the rational zeros theorem, you could take this function and discover that it factors beautifully like this. And it's actually, I want to sort of pay attention to both of these. I'm going to go now back over to Desmos so we can look at some nice graphs. So give me just a second again. Switch cameras. Perfect. And share my screen. All right, let's go over here to Desmos and take a look at what we've got going on. So the graph that I had in the factored form looks like this. And I just want to look at it and notice some cool things about it. Oh, that doesn't belong up there. X plus 1, X. That was really going to look funky there for a minute. Okay, so here is the graph as it stands. And as you can see, it kind of goes a little bit off of the screen. So I'm going to zoom out just a little bit to get a little bit better view of this. There we go. But here's what I want to notice. So in unfactored form, that function began with an x to the fourth. X to the fourth, the graph of just simply y equal x to the fourth is kind of an exaggerated parabola, like we've seen before. And what I want you to kind of notice here is that this shape, if you ignore this wiggliness in the middle, kind of has that general shape of a parabola that you would expect to see of x raised to an even power. So that's kind of interesting. Now I notice that this graph has some x-intercepts. I actually wanted to zoom back in so I can see them a little bit more carefully. They're really easy to see where they are right here. Notice that they are at -1, 2, and 4. And those are precisely the zeros of the polynomial function. And you may remember we've talked about in the past that the zeros of a function are the coordinates of the x-intercepts. So that's important. So there's a lot of clues you get about the shape of this graph by looking simply at the leading coefficient, which is x to the fourth, and the location of these x-intercepts. Now I want to look at the x-intercepts. Oh, by the way, we can also find the y-intercept. That's always a nice thing to do. I'm going to zoom out so I can see where that is a little bit more clearly. 0, -16, pretty far down there. Okay. Zoom back in. I want to look a little bit more closely at these x-intercepts because notice that the graph behaves a little bit differently at this x-intercept as opposed to this one as opposed to that one. Here's the language I want to use. At this x-intercept, I want to say that the graph passes through the x-axis. It starts on one side and goes through to the other side. Same over here, the graph passes through the x-axis. But here, the graph does not go through the x-axis, it touches the x-axis. And if you could focus in on just this little bit of the graph, notice how it's kind of parabola shaped. Whereas over here, this little piece of the graph looks kind of like a straight line, and this little piece of the graph looks like a straight line. If you just focus on just really close to the x-intercepts. Now look back at the equation, and I want you to see if you see a parabola and some straight lines. Look right here, x minus 2 squared. If that were all by itself, it would be a parabola. It corresponds to the parabola-looking shape that happens at this x-intercept. Also, x plus 1, if there is nothing but that would be a straight line, and I want to notice that at that x-intercept, the graph looks like a straight line. And likewise over here at this x-intercept, the graph looks like a straight line. So this is very, very important. The exponent on the factor, which corresponds more elegantly to the multiplicity of the 0, tells you whether the graph will touch the axis like a parabola or cross through the axis like a line. Where this is even, where the exponent is even, the graph will touch the axis like a parabola. Where the exponent is odd, here the exponent would be 1, the graph passes through the x-axis like a line. I'm going to say that that is going to be enough information to get a sketch of a graph like this by hand. It won't be perfect, but a pretty good sense of the idea of the shape. Now I want to show you a second example. So for this, I'm going to just briefly need to unshare. Hello again, and I'm going to need to switch my camera again so I can show you what I want to look at next. All right, magically expose the next line here. I'm going to look at a second function, and I want to see whether anything that I have observed about the graph of the first function might carry over here. So let me go back to Desmos, and we're going to graph that function. We're going to leave that one in factored form so I can show you. So we're going to go back to the other camera. I am going to share my screen again. And we're back here. Let's change the function. Get rid of that one and write in the new one, which is this. Y is equal to negative 2x times x plus 2. It's kind of fun to watch these evolve. Squared times x minus 2 squared. And we have one more exponent to put in. There. Okay. And I'm going to need to zoom out a little bit so I can see the high and low points of this graph. Pretty high up and pretty low down. All right. Now, suppose that I had multiplied out this polynomial. I want to just think about what this would look like if I multiplied it out. Now, I don't literally want to do that, but that would involve, for example, taking x plus 2 times x plus 2, and then x minus 2 times x minus 2, multiplying those, distributing the negative 2x. But I think if you think about it, you might recognize that, generally speaking, the first term, the leading term of that, is not too hard to figure out. If I take the x plus 2 squared, the x plus 2 times x plus 2, you'll notice you'll get an x squared out of that. You'll also get an x squared out of this. So you have an x squared times an x squared. So that's an x to the 4th. And then you have this x up front with a minus 2, which is kind of important too. That will give me an x to the 5th. So I want to say that I believe this graph might have some resemblance to minus x raised to the 5th power. That's in green. Do you kind of see that there? So remember that an odd power of x would give you a wiggle shape. And because of the negative up front, oh, you know what? I think I'll even put the 2. I think it'll make it even more precise. Yeah, how's that look? Even more so. Okay. If you look at the leading coefficient, that will give you a sense of shape. The x to the 5th will give you a wiggle, and the negative sign will tell you that it's reflected over the x-axis. So instead of the wiggle going bottom to top, kind of like that, it'll go top to bottom. And now I want to delete that graph so I can focus on my original. This is all nicely factored, so the zeros of the polynomial are obvious. Let me zoom back in for a closer look. Notice that I have a 0 at -2, +2, and then I also have one at 0. If I were to set 2x equal to 0, I would get 0. So there's an x-intercept at 0, there's one at -2, there's one at +2, and notice the exponents, which refer to the multiplicity. This one is raised to an even power. That would correspond to the x-intercept at -2. So because the exponent is positive, the graph will touch that x-intercept like a parabola. The same will happen at +2. It'll touch the graph like a parabola. However, at 0, which is the x-intercept I'd get from the -2x part, that exponent has the exponent there is an exponent of 1, so the graph will pass through the axis like a line. Anywhere the factor is raised to an odd power, the graph passes through the axis like a line. Everywhere it's to an even power, it touches the graph like a parabola. So if I can go back, and now we're going to try to do some of these by hand. I'm going to go back here and stop sharing and switch the camera back over to my hand camera again. Oh, hit the wrong button, sorry. There, okay. I have some observations that I want to make, and then I want to use those to draw some other things. So, what to watch for? The end behavior of the graph, how the graph looks towards the end, is going to be dictated by the leading term, whatever that is. You want to look for those. You want to pay attention to the x and y intercepts. The x-intercepts will correspond to the zeros of the polynomial. And you want to pay attention to the behavior of the graph near the x-intercepts. And that depends on whether the multiplicity of the 0 is even or odd. Now, I want to put all that together and show you how you can completely draw a graph based on just what we see so far. So let me get where I can show you the equation. There it is. This is the equation I want to graph. Now, let's think about, first of all, the end behavior. And for end behavior, I have to think about what the leading coefficient would be. Now, I don't want to literally multiply this all the way out. That's far too much work. But I do want to think about the leading coefficient, what that would be. And here's the way I think about it. You have x minus 1 squared. So if I were to multiply out that polynomial, there'd be an x squared involved. Multiply by an x plus 1, and there'd be an x cubed involved. Multiply by another x, and you'd have an x to the 4 involved. And with a negative sign in front of it all, I'm going to say that this graph will resemble, at least out towards the edges, there might be doodads in the middle, that it'll look like y equal negative x to the 4th. Now, because of the even power here, this is going to be parabola shaped, just more flat near the origin and more stretched out on the edges. The negative sign reflects it over the x-axis. So the general shape of this graph, I think, is going to look something like that. Let me get my hand out of the way so you can see. Sometimes people say, because there might be wiggliness in the middle, just focus on literally what happens at the end. So that kind of shape on this side, this kind of shape on that side. Now let's see what else we can observe. So I'm going to focus on, first of all, finding the x-intercepts. The x-intercepts are just the zeros of the polynomial, and I can look at my polynomial and see clearly what those are. If I have the factor x plus 3, then the 0 that corresponds to that would be negative 3. That would be right here. So there's a 0 of the polynomial right there. X plus 1 corresponds to a 0 of negative 1. Or think about it this way. Set x plus 1 equal to 0. What do you get? Negative 1. X minus 1 squared would give me a x-intercept right there. It's not a bad idea to figure out where the y-intercept is also. I'm going to put that over here. And if it's not too outrageous, we'll go ahead and graph this as well. Remember that the y-intercept is found by letting x equal 0. So you're really just asking what is f of 0. And if I plug in zeros everywhere, notice that I'd have a negative. The first factor would give you a 3. The second factor would give you a 1. And the third factor would give you a negative 1 squared. Negative 1 squared is positive 1. Altogether, that would give you a negative 3. And not being some outrageous number, we can go ahead and graph that. Sometimes I'll let you know if the exponent if the degree of the polynomial function gets really huge, that y-intercept might be at like negative 39, and it's just not realistic. Now, I'm going to say that that's enough to draw this graph. And you might say, that's just insane. How can that possibly be? Well, let me talk you through it. So I know that the end behavior of this graph is going to look like this. So as I read the graph from left to right, I'm going to be approaching this line. I'm not going to draw it yet. I'm just going to draw it with my, sort of picture it with my hand. It's going to be coming up like y equal negative x to the fourth would be. I hit this point. Looking at the point, oh, that's my cat's having an argument, sorry. That corresponds to this factor. It's raised to an odd power, which means that at that x-intercept, the graph will pass through that point like a line. Now it somehow has to turn around and come back and hit this x-intercept. That one corresponds to x plus 1, which is also raised to an odd power. So at that x-intercept, the graph will pass through the axis like a line. I got to come down and hit this point because I know that's a point on the graph, and then I got to come up and hit this point. But at this point, that corresponds to this factor, and that's raised to an even power, so the multiplicity is even, which means that the graph will just touch that point like a parabola. So at first you might think, oh, I see what's going on. It's just going to kind of keep going like this. But no, it's going to have to come up here and turn around like a parabola and go back down. Let's see if we can put all that together. Now, bear in mind, this is a rough sketch, so we're not looking for perfection here. The graph will come up like this, pass through that point, have to turn around, pass through that point, come down and hit this point, turn around, come up and hit this point, which that one it has to hit like a parabola, so it's going to turn around again and continue on like that. So, passes through the axis because of the odd exponent, passes through the axis because of the odd exponent, touches the axis because of the even exponent, and look at the general overall shape of the graph. It does indeed resemble that end behavior. And notice I didn't plot 1,000,000 points, just those few were enough. Let me see if we can do another one. Just get the hang of that. Oh, let me make this point. So, how did I know to make the graph stop here? How do I know that the graph maybe didn't go a little bit higher? Or maybe not quite as high? Well, the fact of the matter is, at this stage of the game, you really won't know. You'll need some techniques from calculus to know exactly where that highest point might be. And obviously, we're not in a calculus class, so you might discover that at a later time. In this class, we are focusing on basic shapes. If we have a basic shape, that will be good. And actually, you'll see if you're using my math lab that many of the graphs are multiple choice, which means as long as you have the general shape, you find the closest match. All right, here comes another one. Get this all centered and everything. All right, hope that isn't making you dizzy. All right, let's look at this. So the issues are end behavior, that's number one, where the x and y intercepts are, and then what is the behavior at all the x intercepts. So imagine again that you're going to multiply this out because you need to know what the leading coefficient is. Because of this squared here, there'd be an x squared, but then times another x would mean there'd be an x cubed, and times two more x's means the general shape will resemble, y equal x to the fifth. Yeah, there's that 2 up front, but that doesn't really matter too much as far as the shape. There's no negative sign. That's important. Remember, the last one had a negative sign, which had the effect of reflecting it over the axis. Y equal x to the fifth has a general shape like this. It's a wiggle shape. Or the way some people prefer to write this, just because of the wiggliness in the middle, they'll just say, well, it kind of acts like this on this side, and like that on that side. And that's fine too. You'll see that. So I know my general shape looks like that. I need to figure out where my zeros are next. So I look at each factor, and yes, the 2x squared is a factor. You want to ask, well, where is 2x squared equal to 0? Or if you need to, you could think of that as x minus 0 squared, which helps me see that the 0 that corresponds to this factor right here is right at the origin. X minus 2 means there's a 0 at positive 2. X plus 2 means there's a 0 at negative 2. Those are the x-intercepts. Now I'm also interested in the y-intercept, which I get by plugging in a 0. But you might notice that if I plug in a 0, I'm just going to get 0, and that's that point right there. That's the y-intercept. So if you can believe it, I can draw this entire graph by nothing other than these points. Okay, so let's talk it through. I don't want to draw it first. I want to just sort of visualize it. So because this is my end behavior, I'm going to be coming up from the bottom like this. When I get to this x-intercept, I figure out where does that come from. So that's an x-intercept of negative 2. It corresponds to the factor x plus 2 squared. That is squared, so that means as I approach that x-intercept, I touch the axis like a parabola. It comes up and goes down. Then I have to somehow reach the next x-intercept, which comes from this factor, also raised to an even power. So as the graph approaches this intercept, it will again touch the axis like a parabola. But as I get to this factor, x minus 2, that corresponds to this x-intercept of 2, odd power. Now the graph will pass through that intercept like a line. And if you think about it, that means it will be leaving the graph kind of like this, giving me that general overall shape that I want. So let's see if we can make this happen. We traced it by hand, but again, being more careful. We're coming up from the bottom like this because of our end behavior. As I get to that x-intercept, because the multiplicity is even, I touch the axis like a parabola. I can't go very far because I got to come back up to this point. So I go down a little bit, back up. This one again has even multiplicity, so I touch the graph. And I go back down, but not too far because I've got to come back up and hit this point. But at this point, with the odd multiplicity, I pass through the axis like a line, and I continue on to give me a rough shape that does correspond to the end behavior I was thinking about. Isn't that cool? Now this will take some practice, but it's a nice little, almost like a puzzle that you get to play. Now I have one more example to do, and this one's a little bit more involved. I have some graph paper coming up, but on this one, I wanted to do one not in factored form. In some ways, not having it factored form is a good thing because I don't have to imagine what the function would look like if I multiplied it out. I know, I can see right here. And the end behavior is going to be dictated by that first term. So the end behavior of whatever I'm going to draw is going to look like negative x cubed. Now we know that x cubed is a wiggle that goes from bottom left to upper right. This negative sign makes it reflect over the axis. So the general shape of this graph is going to look like that wiggle turned upside down. So the overall general shape will kind of look like that. Or if you kind of like, and you'll see this lots of time, just to focus on literally the ends, the end behavior would look like this, like negative x cubed. Now, but in order to do anything more with this, I really have to get it in factored form. So a couple points. So first thing, if your leading coefficient happens to be a negative, the easiest or the best thing to do is to factor out that negative sign first. So just factor out the negative sign, which in parentheses would mean all the other signs would reverse. So x cubed minus 3x squared minus x plus 3. It would be really awesome if I could factor this, and I can. It's a polynomial, which means that I could use an old friend I've learned not too long ago called the rational zeros theorem to attempt to factor this. Now, while I'm doing this, just sort of let this negative sign go along for the ride. It just sits there. I'm going to focus all my attention on just the parabola. And if you remember the rational zeros theorem, what you have to do is you have to look at the factors of the constant term. My constant term here is a 3, and the factors of 3 would be 1 and 3. And also the factors of the leading coefficient, whatever coefficient comes up front. Again, don't forget we're just factoring out that negative, so don't worry about that. Right in here, the leading coefficient is a 1, and the factors of 1 are, well, 1. Then the possible rational zeros have the form plus or minus p over q, where p is one of the factors of 3 and q is one of the factors of 1. So there's not too many options here. It's either going to be plus or minus 1 over 1, which is 1, or plus or minus 1 over 3, which is 3. These are the possible zeros. I don't know which ones they are, but these are the possible zeros. Now what you do is you just try those out using synthetic division. There's a little more space here. Let's just see if we get super lucky and if the first thing on our list happens to be a 0. So I can do this by synthetic division. I'm going to put the number 1 right here because that's what I want to plug in. And I'm looking at the polynomial that I'm wanting to evaluate. And again, that does not include that negative sign. That's been factored out front, so don't worry about that. Just write in these coefficients of the remaining polynomial. And let's check that out and do synthetic division. So I will copy the 1, and then 1 times 1 is 1. Add down the column, that gives me negative 2. 1 times negative 2 gives me negative 2. Add down the column gives me negative 3. 1 times negative 3 gives me negative 3. And then add down the column, you get 0, and we got super lucky. That's a 0 of the polynomial right there. So remember, not only does that tell you a 0, it tells you more than that. If 1 is a 0, then x minus 1 is a factor. So if I went all the way back to my function as it originally stood, this is my function. Remember the negative sign up front. I'd have a factor of x minus 1 to correspond with this. And that would be multiplied by the quotient that comes out of the synthetic division, x squared minus 2x minus 3. And because that one is quadratic, I can just factor that by ordinary means, like we've learned a long time ago, and look for two numbers whose product is negative 3 and whose sum is negative 2. I think something like x minus 3 times x plus 1 would do the trick. Now, all of that was in preparation for drawing the graph. And the things I want to pay most attention to is how this factors at the end and the fact the leading coefficient dictates an overall end behavior like this. Now let's get some graph paper and see how this turns out. Here I've written my function in its factored form just because, so we don't have to go back and think about it. Remember the end behavior though. And now let's locate all of our intercepts. We know that because of the x minus 1, there's an x-intercept at 1. Because of the x minus 3, there's an x-intercept at 3. It goes nice and big. And because of the x plus 1, there's an x-intercept at negative 1. Probably worth our while to find the y-intercept as well. And that is found by letting x equal 0. So what is f of 0? And I can plug it in right here, or I can go back to my original. Either way is just fine. This would give me a negative. And if I put a 0 here, that'd be negative 1. 0 here would give me negative 3. And 0 here would give me a 1. Negative times negative is negative. And it looks to me like it's a negative 3. And I'm going to plot that point as well. Now, this ought to be enough, especially if I think about the multiplicity of the zeros. Notice that all these exponents here are 1. So the multiplicity of all zeros is 1, or 1, whichever. And that means that every time I approach an x-intercept, the graph will pass through the axis like a line. It will not touch it like a parabola. Now the end behavior, again, you might remember from the previous slide. Actually, that went off the top. Looks like this. So you'll be coming in from up above. We'll do this by hand, by visualizing first. Pass through the axis. Got to hit this point. Come back and hit the axis again, but pass through it. At some point, it'll have to turn around to come back through and hit this point and pass through it and keep going. And that would match our end behavior just fine. So it'll be something along the lines of this, coming down through the axis, turning around, going back up through the axis, turning around, going back through the axis, and continuing on. And that is roughly the shape that we have. Now anyway, I hope these examples are really, really helpful. They make the sketching of a rational function very easy. I think before we leave this, let's do this last one on Desmos where we can get like a super nice drawing. So I'm going to switch my cameras again and share my screen. And go back to Desmos. Let me copy in the function as we had it. And if you will trust me on this, this is what it looked like. It was negative x to the third plus 3x squared plus x minus 3. And that, I think, looks a whole lot like the graph that I drew. The one thing you might notice is I sort of guessed at that the lowest point would be right here at 0, negative 3. It actually goes a little lower. Oh my goodness, look at that. You will not know how it knows that until you have some calculus. So we are just concerned about the general shape, which we have, and the exact high and low points. Well, we don't have that right now. So give this some practice. I hope you'll find this. I think these are actually a lot of fun. And try some and see how they go. And I wish you all the best.